This video is going to take you through creating a resizable array in C. Now this video isn't for every skill level, so I've listed the prerequisites here. You should probably have a good understanding of pointers, stack and heap memory, which also has to do with pointers, and also the malloc and realloc functions, define statements, and then finally structures. I've included a list of resources in the description for all of these topics. But anyways, let's get started. So if you've worked in any higher level language, such as Python, we're going to go ahead and enter the interpreter here, and we'll say we want to create an array. We're going to put 3 elements in this array, and we'll print it. Nothing new. The cool thing about a higher level language such as Python is the fact that you can do this, array.append, and we can add a 4th element. We'll print that array, and you can see we seamlessly created another element in this array. Now this isn't so easy in C. If we wanted to do that, we really don't have a method of doing so. So let me shrink this a little bit. I'm going to go ahead and put my include statements. Create the main function. And now we'll define an array. We want an integer array. And we'll say we'll just have an inherently defined size of this array. So however many elements we initialize it with is how big the array will be. Now we could also say something like an array of 5, and that predefines the size of the array holding only 5 integers. But we'll go with just the non-explicit way. So we'll create the array. And you can see we've done the same exact array, and then to print it, I want to say loop through a for loop while I is less than the size of array, and we'll define that in a second. We'll print each integer at the index of I. Give spaces between them. And then finally, just a new line for clarity. So we have to figure out what the size of this array is in the first place. And the way we do that is declaring a variable size of array equal to size of. This is a function within the C libraries. We'll say the size of the array, which is going to give us the number of bytes that this array is, and we'll divide that by the size of an integer, because that's what we're using inside of our array. So that's going to give us how many integers are in our array. We'll go ahead and print that out for clarity as well. So we should be able to run this at this point. So let's go back to the terminal, exit out of the interpreter, and compile our file. Okay, now we have an executable, a.out, so we'll do /a.out, and you can see we have a size of 3, and then the elements are 1, 2, and 3 in this array. Now the problem in C is the fact that we don't have that .append function. We're not able to just come down here at the end of our program and say array.append 4. We can't do that. It just doesn't work. We don't have that functionality. So wouldn't it be nice if we did, though? And this is an interview question that comes up a lot, and so we're going to actually define our own resizable array so that we can have that exact same functionality that Python does. In order to create this resizable array, we're going to have to come up with a structure that allows us to keep track of our max size of the array, the current size of the array, and the pointer to the allocation of heap memory that we're using. So let's go ahead and clear out this entire main function. We'll come back to that. I've also created a couple other files, an array.h file and a resize.c file. So this file here is going to keep all of our functions. This is the basically the functionality of this resizable array. Then we'll have our structure sitting in array.h, and then the resizable array.c will be the main program. So let's come over to the array.h, and we'll define, well, let's just call it size 10. So this will be the initial size of our array. Now we're going to define a typedef struct, and inside that struct we'll have an integer called current size, another integer called max size, and then finally an integer pointer that points to an array of integers, and we'll call that just our array. And then we'll refer to this struct as our array for a resizable array. Okay, so that should work there, and we'll come over to our resize.c and get all the libraries set up. We'll include our .h file. And now for our first function, we're going to just call it init array. And inside, this is going to take the parameter of our struct. So we'll say, remember we called this the R array. So we'll say R array, a pointer to this that we'll call just RA. Be pretty simple there. And what we'll do is we'll say RA current size equals 0, RA max size equals size. Remember we defined this as a macro up at the top of our .h file, and this variable here, size, is accessible because we included it here. And then finally, we're going to say RA array equals, and what we're going to do is allocate memory. So we'll say an integer, cast an integer type from alloc, and then we'll say size of an integer times our size of the array. Okay, so that should do it for the initialization of the array. Before we get too far with all of our functions, let's go ahead and test this to make sure that it's all working with the three files. One thing that I notice right now is we're going to have to add a star here because we're making memory for a pointer, because we have defined our array as a pointer. And then we're also going to have to come over to the array.h file and define our prototype. So our function, we can just basically copy it. So now we have our prototype, put a semicolon at the end to finish that sentence, and then we can come over to our main function and start defining things. So let's remember what we did. We created a struct called R array, so we're going to want to initialize that as RA, and then we'll call the function init array, and we'll pass in the address of RA to that function. So what that's going to do is it's literally just going to create one instance of this structure, and the current size is going to be 0, the max size is going to be size, which is 10, and then we'll have a allocated pointer that holds enough memory for 10 integers. Let's now go back to our main program and start defining things. We called this R array. This is the name of the struct. So we'll define our array, and we'll just say an arbitrary variable name RA. So we've defined it. Now we need to initialize it. So we'll call that function init array, and we'll pass in the address of RA so that it can be modified. Now let's actually put some values in there so that we can see how this is working. So the way we do that is say RA dot, and notice that I'm using the dot operator rather than this arrow operator because we're working with a struct. We're not working with a pointer to a struct. If you see over here in the init array function, this RA is actually a pointer, so in order to access the items within that struct, we have to use this arrow notation. But over here in the main function, we're using just the struct itself, not a pointer, so we use this dot notation. So just wanted to clear that up. So we'll say RA dot max size, or actually no, we've already got that defined. We'll just go straight to our array. So right here, this call right here is basically giving us the first element of the array. But we'll go ahead and explicitly define that and say RA.array of 0, so the 0th element, and we'll say that equals 300, something like that. Then just for making this example a little bit bigger, we'll say the second element is 500. Okay, so now we'll print all this out by saying, first we'll say the max size, then we'll say the current size, and then we'll say first element and second element. Okay, and then we're going to come down to the next line here. It's getting pretty long. And so our max size is represented by RA.max size. Our current size is RA.current size. And then our first and second elements are RA.array of 0 and RA.array of 1. So this should complete that statement, and if all goes well, we should be able to visualize what we've just created. So let's go over to the terminal, and we will compile everything. So GCC resizable array.c, array.h, and resize.c. And oh, I did not put spaces in there. Just a space there maybe. Okay, awesome. So now we have our a.out executable. We'll do /a.out. And we can see that our max size is 10 as defined in the init function. Current size is 0. And then our first and second element are 300 and 500 respectively. Now that we know that everything is working correctly, we can go ahead and create the functionality that we're looking for. So we're going to come over to the resize.c file where we keep our functions and create a check function. This function is going to check the size of our array that is contained within the structure, and if there's not enough room to append another item to the array pointer, and I'm talking about this little pointer right here. So we're going to say if the current size is greater or equal to the max size, then we probably need to extend the size of this pointer and reallocate memory. So how we'll do that is come over to this check size function. We'll say if RA max current size is greater or equal to RA max size, then that means we have to reallocate memory. So the first thing that we're going to do is update the variable max size. So we'll say array max size multiplied by 2, and then we'll reallocate the array that we have by saying realloc. We'll pass in the array as the first argument, and then we'll say the size of an integer times our new max size that we just updated above. And this function should now work correctly and reallocate the size if it's not big enough. The next function we need to do is called, we will say append array, and what we're doing here is passing in our struct again, and then we're going to pass in a value that we want to append. So first off, we need to check the size of our struct to make sure that it's the right size, and if not, we need to double the size. And then after we've done that, we can append the item, the value here, to the end of the array. So we can come down here and just say array of current size equals value, and then we want to increase the current size by 1. Lastly, we need to define a free function. We'll free the array. We're just passing in pointer again, and we're just going to say free array. So that should work all right for us. Let's test this now in the main function. So we've created our array. Now we need to append. Well, let me see what I name this again. Append array. Now we can append array and say we need to give it the address of our structure, and then we'll say a value of 5. So now after that append, we should have the first element will be 5, and then we'll say append array again, and we'll call this one 10. So if all goes well, this right here should be printing out the first element as 5 and the second element as 10. And then at the very end, we're just going to call free array and pass in the address of that. So let's see how that works. We'll go ahead and compile everything again. Okay, so we have just a couple errors here. The first couple are just saying that we didn't prototype our functions. So let's go ahead and do that. Forgot to do that. So we'll copy the definitions and paste them over into our .h file. So that should take care of that. And then also, I forgot to define a couple things here. I was just saying the current size. I need to actually tell it where that current size variable is coming from. So that might fix the problems. Okay, so this should work now. We can see that our max size is 10. Our current size is 2 because we've added 2 elements. And our first element is 5, second element is 10. So the last thing that we should probably do, we've checked that it's loading values in there correctly with the append function. We haven't checked to see what happens if we try to append items over the storage limit. So again, let's remember that we created an initial size of 10. So if we create a for loop that says we're going to go until I is less than, while I is less than 15. So 15 exceeds that limit, so obviously we're going to have some sort of this function that we created here, the check size, is going to activate once we reach a value of 10, or it should at least. So what we can do is do the for loop, and for each for loop we'll append array, and we'll pass in the address of RA, and we'll just say a value of 30, something, doesn't matter. So what this will do is basically say 15 times we're going to go through this for loop, and each time we're going to append to the array that we have. So to illustrate this even further, we're going to print at the end the, let's see, the RA max size and the RA current size. So we'll say max size is to take this further, we'll put this at the very top before we've looped through it and extended the array. So what should happen here is when we init the array, there's nothing in it, and then when we make this print statement, we should get a max size of 10 as defined by our size 10 inside the init function, and we should have a current size of 0. But then we go through the for loop and we append 15 items to 15 items with a value of 30 each. That's just an integer we're putting in. And then when we print this last statement, the max size and the current size should have changed. So the current size should be 15, I believe, and then the max size should be 20, because in our check size function we multiply the max size by 2 if it exceeds the space that we have. So let's try that out. And what I've done wrong here is tried to identify these with the pointer notation, even though I tried to explain that earlier in the video. So we'll clear that up and try again. We can see here exactly what we expected. The max size is 10, the current size is 0 before the for loop, and then after the for loop our max size is 20 and our current size is 15. Alright, so that completes the program. You can find all of this code on the GitHub listed in the description. But before we end this video, let's just do a quick talk about the time complexity of this. So it's a little bit confusing, but the amortized runtime of this specific program is actually O of 1. So we'll write this out real quickly. Okay, so that's the runtime. But why is it not O of n? So to illustrate this, let's say that our start size equals 2. Now when we check the size to make sure that our current size is not greater or equal to this max size or the start size, we're going to get to append 2 times. So we'll call the append function once, twice, and on the second time we're going to have to double the size of array. But then now our array is size 4 because we've doubled from 2 to 4. And so now we can append 2 more times to get up to 4, so we're doubling again. So now our size is 8, and so now we can append 4 times, and so on and so forth. And on this 4th time, we double it again, and now our size is 16. So you can see as this gets bigger and bigger, the amount of times that we actually double the size of our array gets decreased over time. So although the runtime of each of these append functions, where we have to double the size of the array, is O of n, the amortized runtime, if you aggregate over all of the operations, is going to actually be O of 1. So that's just a little snippet on the time complexity of this algorithm and or functionality. I hope that you enjoyed and learned a lot from this video. Thanks.